So today we have Andrei Smilga from Nantes, and he will tell us about higher derivative systems, classical and quantum versions. So off you go, Andrei. Go ahead.
Okay, so thank you, Andreas, and thank you for, giving me the chance to talk here. You know, I written a couple of papers on this PHHQP stuff about 10 years ago, more than that. Then I'm doing mostly other things. Last time I went to the meeting, the conference PHHQP that was in Algeria 6 years ago, and I made there the talk on exactly this subject, right? So why I'm talking again? There are two excuses. The first excuse that my recollection is that the microphone didn't work properly in Algeria, and so it was difficult probably to follow my talk. And the second excuse that since that time I've written kind of review about this stuff, and so my talk is mostly based on this review. Okay, so first about motivation, why it was interesting for me, why I personally studied that. Well, here that's very well-known citation from Isaac Newton, everybody knows that. And then you can say that in the time of Newton, indeed, he was on the shore of great ocean, but now we know a lot of many things, which is true. But still, in terms of energy, right, we exploded until this scale, and the Planck mass is 16 orders of magnitude larger, right? So that's the part of the ocean that we explode. We are still pretty much near the plage, right, near the beach. Okay, and we cannot study it experimentally, such large energies, and we can try to, to guess by pure logic how the nature is made. And here the most serious problem is the problem of gravity. Everybody again knows that. And often people say that the problem is that Einstein gravity is not normalizable. Well, this is a problem, but there are problems which are, how to say, more pertinent. That first of all, non-causality of gravity, inherent non-causality, because the space and time are dynamical variables. So it's not like Cauchy problem. We cannot pose the problem that differential equation developed in flat space. Well, everything is intertwined, space and time also are in the game. As a result, there are some paradoxes. For example, even in classical gravity, there are solutions with closed time loops, so-called Gödel solutions. And that means that you can go first forward in time, and then you find yourself back in time in the past. You can kill your great-grandfather, and that would be not only criminal, but also paradoxical. So what to do? And the most popular, how to say, the most popular theory in the market is string theory. People think that grand unified theory of everything is some variant of string theory, but there are again problems. Actually, at the fundamental level, string theory is just not formulated right now. Like field theory, so you have functionals which depend on string position and the dynamics of this functional. You don't describe string theory, you cannot describe string theory in this language. Then there are no phenomenological successes. Then there are also problems with some divergences and to the best of my knowledge that they are not completely resolved. And now, since a long time, I was thinking about another possibility. The fundamental theory of everything is a field theory formulated in flat space-time. If you formulate something in flat space-time, then you don't have problems with causality. You have light cones which are straight, and you cannot go into the past. Also, please, I'm talking, but the more questions from you, the better for me, and I think for you also. So right now, that's kind of introduction, well, philosophical introduction, but later, if something is not clear, please just immediately ask questions. And so this dream solution, another variant of the theory of everything, is that it is formulated in flat space-time, but this flat space-time has larger dimension, not 4 but more. And then our universe is like classical solution in this higher dimensional theory. And the gravity is just an effective theory on this 3-brane, what people say. Like, for example, one compare it with the soap film. The fundamental theory of soap is 3-dimensional. But you can go on the soap film and write the effective Hamiltonian, which is just surface tension multiplied by the area. And it looks already like gravity, right? So you can write it as a cosmological term for the gravity. And so something like that, that's my act of faith, if you want, should happen in a real universe. But then you have a problem. For example, you try like Young-Mills theory, but in 6-dimensional space-time. And then immediately H carries dimension, and the theory is not renormalizable. Not renormalizable, it's also bad. Maybe causality is there, but non-renormalizability means, among other things, that you cannot give a constructive definition of the functional integral. You cannot put it on the lattice, and the limit, you can put it on the lattice, but the limit when the lattice spacing goes to 0 just doesn't exist. What can you do more? You can make coupling constant dimensionless, but then you should add extra derivatives. For example, you can try that. Here you have dimensionless coupling constant, and this theory is even renormalizable, but it includes higher derivatives, and then immediately the ghosts appear. And so one should understand how to read them, the ghosts. So what are ghosts? My definition is that it's a system where the Hamiltonian doesn't have a ground state. It doesn't have the state with the lowest energy. Also, it doesn't have a state with the highest energy. There are the states all the way from minus to plus infinity in the energy. So there is no vacuum, and we are used, when we are doing field theory, we are used to a theory when there are vacuum and the particles are excitations over this vacuum. So it's very much unusual, but it's inherent in any high derivative theory. Now, I will go back to field theory in the very end of the talk. And now I will just remind you some facts from classical and quantum mechanics of the systems with high derivatives. And so I start with so-called Astragaradsky Hamiltonian. Astragarsky was a mathematician, Russian mathematician, and he is known by several things, several results in mathematics he obtained. Well, I know, and you also know Astragadsky theorem or Gauss-Astragadsky theorem from vector analysis. Then there is some clever method of calculating the integrals of the ratio of two rational polynomials, Astrogradsky method, and finally Astragarsky Hamiltonian. So he published it in this paper in 1850. As you see, this paper was in French. Because Astragadsky knew well French, he worked in France as a postdoc. He was in France, and for example, his Astragadsky theorem he well worked out in that time when he worked in France. And in this paper, what he did, he reinvented Hamiltonian formalism. At that time, English was not yet common language of science, and Astragadsky just didn't know about the works of Hamilton because they were published in English. And so he just reinvented it and applied also to high derivative theories. So he constructed Hamiltonians for high derivative systems. That's what he did. Now I will just explain how it's done. So we start with some Lagrangian, which, for example, depends not only on position and velocity, but also on acceleration, on x double dot, right? Then the Lagrange equations of motion from the least action principle are that they involve, well, not only these two terms, but also this term, which eventually gives rise to fourth order time derivative, right? Now, there is no explicit dependence on time, and so there is conserved energy. So just this quantity is an integral of motion. Okay, now to construct Hamiltonian, you introduce extra variable as consider velocity as an independent variable. And then there are then two variables, x and v, and two canonical momenta. The canonical momentum corresponding to v is just the variation of Lagrangian over v dot as usual, and the canonical momentum which corresponds to x is a little bit more complicated. It just comes from this bracket. So that's canonical momentum for variable x. Then the canonical Hamiltonian, Astragadsky Hamiltonian, has this form. Now this a is acceleration, so x double dot, and you can express it via canonical momentum to v, to via x and v, exactly from this definition. You just resolve it for acceleration and plug it in the Hamiltonian. That's Astragadsky Hamiltonian. Now, you see the linear term. So px x dot, or which is the same px multiplying v, right? So it's linear, and it can be positive and it can be negative. And that means that the energy of the system is always as much positive as you want, or as much negative as you want. I think that was known. Astragadsky, incidentally, didn't study dynamical issues. He just has proposed general method to write Hamiltonians. But there was a paper of Pais and Uhlenbeck back in 1950, and they, I think, already understood that the energy is not bounded from above or from below. And as a theorem, it was formulated by Woodard rather recently. That's classical version of the theorem. That classical energy is maybe very much positive and very much negative. And that's the quantum version of the theorem, of this theorem. Well, it was proven that the spectrum of quantum Hamiltonian is not bounded neither from below nor from above if your original, so it works for any non-degenerate high derivative system. So if high derivatives are really there, indeed there, then there is no way out. The Hamiltonian is not bounded. There is no ground state. Now, just a little philological remark, if you want. Sometimes this phenomenon is called Astragaraski Instability. That's the term which was set and used by Woodard. But I don't like it, first because it's not instability. And when you pronounce the word instability, you think about a ball on the top of the hill, which is stable, but once you just touch it, it starts to roll, and the deviation, grows exponentially, right? So it's not instability in this sense. And then it was not noticed by Astragradsky, this phenomenon. Astragradsky, as I told you already, he just written the Hamiltonian. He didn't study the dynamics of this Hamiltonian. And of course, that's a gold-plated manifestation of Arnold's principle. Well, here it's written this principle. And of course, it's self-referential. It applies to Arnold's principle too, right? Okay, so that's some general theorems, and then some examples. And first, of course, we start with Weiss-Uhlenbeck oscillator. That's the paper of 1950, 100 years after the paper of Astragradsky. So the Astragaraski Hamiltonian in this case has this form. And you see this linear term which I mentioned, and there are some other terms, and it's quadratic. It's more complicated than the Hamiltonian of standard oscillator, but it's still quadratic. So the problem is solvable in classically and also in quantum mechanics. Now, if omega-1 is not the same as omega-2, one can make canonical transformation to some other variables. So this large x, and large p, right? That's how they express their original variables, x, v, and corresponding canonical moment. And if you do this canonical transformation, then the Hamiltonian acquires a very simple form. It's just two harmonic oscillators. The one oscillator comes with positive sign, and another oscillator comes with negative sign. Incidentally, it's interesting that the first person who has written this Hamiltonian and studied it was Pauli, Wolfgang Pauli, and there was a paper in the Review of Modern Physics in 1943. He just raised this Hamiltonian, also the issues like discusses the issues like indefinite metric and things like that. Now the spectrum, of course, is known, and it can be positive and negative. Now, if you're just each eigenstate, which is corresponding to this eigenvalue, is normalizable. So mathematicians say that it's pure point spectrum. And if the ratio omega-1 to omega-2 is rational, then each level is infinitely degenerate. And if this ratio is irrational, then, when it's everywhere dense. So in each, however small interval of energies, there is an infinity of eigenstates. However, each such eigenstate is normalizable. Now, what is interesting is to look at what happens in degenerate case when omega-1 is equal to omega-2. In this case, this canonical transformation doesn't work. It's singular, and one should study the original Hamiltonian. But it's possible to do. The result is that the spectrum in this case is continuous. So these eigenstates are not normalizable anymore. So there are states of continuum spectrum. And one can even write explicitly the Eigen Functions. So here I've written it, these Eigen Functions, right? So there are quantum numbers L, which is integer, that's angular momentum. And like angular momentum, the analog of angular momentum, because you see there are two oscillators, right? If you consider two oscillators with both positive energies, then it would be angular momentum. And here it's kind of analog of angular momentum, L. And K is just a real number. Now the energy, you can read it here, there's the energy. And it can be positive and negative as you wish. And so that's unusual. But I want to emphasize that it's not sick. There are no internal contradictions. If you consider only free Pius Uhlenbeck oscillator, then you can solve both classical and quantum problem. You can find the trajectories. And you can find the spectrum, and the evolution operator is unitary. There is no breaking of unitarity here. People sometimes think that the appearance of ghosts necessarily lead to violation of unitarity, and that's not correct. Here, the example of a system which is quite benign in this sense, but of course, it doesn't have vacuum state, is very much unusual. Now, why it's called ghosts? Well, this term came from field theory. You have kinetic energy, which is not positive definite. You have negative terms in the kinetic energy. And that's similar to Faddeev-Popov ghosts, for example, in field theory. And people in field theory, they treated these ghost systems with negative kinetic term, introducing indefinite metric. Why they are doing? Because they want the Hamiltonian to be positive definite. If you want Hamiltonian to be positive definite, no matter what price, then you should introduce indefinite metric. And here is just an example where I explain this. Suppose you have your two oscillators, and these are creation and annihilation operators, right? Now, the ordinary vacuum, which we are used to, is annihilated by A1 by annihilation operators, right? And if you define a vacuum like that, it is in the middle of the spectrum. So there are states with energies which are larger, and the states with the energies where A2 is excited, which are lower. But you can do some other things, introduce some other state, phi tilde, which satisfies this condition, that it's annihilated by A1 and also by A2 dagger. If you do that, and you can consider the tower of states, well, with A1, it's all okay, but you also can consider the tower of states for A2. And you can notice that the energies of all the states compared to the energy of phi tilde are positive. So if you just define that the energy of the state phi tilde is 0, then, for example, for the first excited state, you obtain that first excited state is in this definition A2 times phi dot. Then you obtain that, and then if the commutation relation for A2 dagger and A2 are the same as, well, what we are used to, then this energy will be positive. However, one should pay a price then that indeed the unitarity, the metric is indefinite. How can one see that? Well, one can rename what used to be A2, you can rename as B2 dagger, and what used to be A2 dagger, you can rename it as B2. And then the difference is that the commutator of B2 and B dagger 2 and B2 has another sign compared to the commutator of B1, dagger, and B1. Then, so this, what you obtain, -1 and not +1 as for ordinary system. And as a result, this excited state has a negative norm. Well, one can check it. So that's indefinite metric. Now, if you look at the Eigen function of this state, it looks like that. So it's not normalizable. It exponentially grows at large x2. And so the whole tower of states is not an L2. And so I think, that's my opinion, that it's better not to treat these systems with, in this way, with indefinite metric, but just say that the Hamiltonian is not positive definite. And then unitarity, well, for the free system is there. Then, well, both Carl and Philip are there, and so I will talk about their proposal. Their proposal was the following. So you consider the Hamiltonian, which is the difference of two harmonic oscillators, and now keep x1 positive, but real, x1 real, but assume that x2 is imaginary. If x2 is imaginary, then the states immediately become normalizable, right? And then everything is fine. The states become normalizable, the energy is positive, there are no ghosts. But if you do that, it's not the same spectral problem as the problem you started with. It's just another spectral. For me, there is no real need to do that because the system with x1 and x2 real is also benign in a sense that evolution operator is unity. Now I want to discuss, well, this issue which was not clear for some time and was clarified comparatively recently. What to do with path integrals for high derivative systems. Well, you can write Minkowski path integral for high derivative systems too, and there is no problem with this Minkowski path integral. Also, you can write the corresponding Hamiltonian path integral. So you have xv, px, and pv, and you write Minkowski Hamiltonian path integral like that. Also, there is no problem. Now, if you substitute here Astragaraski Hamiltonian and integrate over px, then you obtain the factor, vector function. That means that you started here where v and x were kind of independent variables. But if you do the integration over px, you immediately obtain that v is actually velocity. V is equal to x dot. Now, if you get rid of another canonical momentum and also the variable v, you of course will reproduce the original Lagrangian path integral. Now, but that was Minkowski path integral. if you want to make Euclidean rotation, replace t by I tau, then you meet a problem. For Hamiltonian path integral, it's just impossible, because once you replace t by I tau, this integral just doesn't converge. It badly diverges, because p and v is real. So for large p, large values of p and v, the integral diverges. One can, on the other hand, try to do to replace time by imaginary time in the Lagrangian path integral, and then this path integral converges. On the other hand, this integral cannot be attributed physical meaning, because if you that's another explanation why you cannot do Euclidean rotation, because the Euclidean evolution operator and also partition function also are not defined. So we are used that energies are positive, and if energies are negative, so it's the sum is not defined. Now, if you do that on the Lagrangian level, then the integral converges. But if you go back from Euclidean time to Minkowski time, it doesn't give you benign Hamiltonian integral. It doesn't give you unitary evolution. So that was understood first, not quite complete, not completely understood. There was a paper by Hawking and Hertog back in 2002, and it was completely understood in this paper with examples. So that's clear now. The conclusion: for higher derivative systems, you just cannot consider Euclidean path integrals. Just cannot. That was until now. That was free system. But we are interested what happens if one includes interaction. And here you meet real problems if you include interactions. Well, consider the pi-Sulenbeck oscillator with equal frequencies, but add a quartic term, right? These are equations of motion. They are nonlinear now. They have fixed point at 0. And one can observe that if the deviation, deviation is not large. What is large, there are some scale parameters omega and alpha. One can work it out. So if the deviation is not large, the trajectories are still stable. So there is some island of stability around 0. However, if the deviation is large, then there is no stability. The system goes astray and hits infinity at finite time. So that's what I call collapse. Here I show the typical trajectory of the system, well close to the shore of the stability island, right? So first there are quasi-harmonic oscillations, and then at some point it just goes astray and hits infinity at finite time, which is bad. Now that was in my paper, this particular example of 2005. There was some other paper a little bit earlier who found a similar stability island, but for another high derivative system. Now, what is collapse? Actually, it's well known in standard textbooks in quantum mechanics, at least in Landau-Lifshitz textbook. There is a paragraph devoted to central potential, attractive potential, like 1 over r squared. And then it was known since the beginning of the 50s that if this coefficient is large enough, well, classical trajectories, they go to zero at finite time. They make like spirals and they go to zero. Spirals, the infinite number of turns, but they go to zero at finite time. Now, if you consider quantum mechanics, then if k is small, it's still benign. The Hamiltonian has a ground state. But if k is large, then the Schrödinger problem is simply is not defined. Spectrum not only is not bounded from below, but also you cannot find the eigenvalues of this spectrum. Because if you regularize this potential, for example, make it something like that, which is constant at some small circle near zero, you can do that, and then the spectrum will have ground state. But not only ground state, but all the states of the spectrum depend on this regularization, depend on A. And so you don't know what is the spectrum in the original theory. And it's not unitary. Well, one can study again this evolution operator, and one can say that the probability kind of leaks into the singularity, right? What is unitarity? Unitarity is the statement that probability of all possible issues of some processes is one. And the violation of unitarity means that it's not one. And so indeed, when it goes into singularity, you lose control and unitarity is violated. But this example teaches us some important thing. You see, this system has collapse for any, classically for any kappa. But in quantum mechanics, the collapse, the violation of unitarity and the absence of violation of unitarity occurs only if kappa is larger than some limit, some threshold. And why is that? It's simply because quantum fluctuations, they kind of cope with this tendency of going into singularity. And if kappa is small, they cope successfully. The spectrum is still well defined. And if kappa is larger than something, then they already cannot do that. And the collapse is there also in the quantum system. So the observation is that one needn't study quantum dynamics of the system to say whether the collapse is there or not. If quantum theory is sick, then classical theory is definitely sick, right? And as classical theory is benign, then definitely quantum theory is also benign, because quantum fluctuations only can, they oppose this ghost effect, non-unitarity effect. So if one finds a benign classical high derivative system, one is sure that quantum mechanically it's also good. And of course, it's much easier to study classical dynamics than quantum dynamics. Now, for the interacting system, which I shown before, the collapse occurs. But a remarkable fact is that not all interacting systems involving a non-trivial interaction have this collapse. There are some special high derivative systems where it doesn't happen. What is written here, it's some supersymmetric action. And for those who don't know what is supersymmetry, just not work in supersymmetry, just don't put attention here. One can derive from here the component Lagrangian and component Hamiltonian. There is some fermionic part, which I don't also write down. And the Hamiltonian derived finally from this supersymmetric action has a very simple form. So there are two real variables, phi and d. Small p is canonical momentum of phi, and large p is canonical momentum of d. And so there's the Hamiltonian. And of course, you see that it's not positive definite. There is this linear term, and it can be positive and negative. So you have four-dimensional phase space. And what is also remarkable in this system, that besides Hamiltonian, there is another integral of motion, which has this simple form. And if you have two integrals of motion in a system involving two couples of canonical variables, then the system is exactly soluble. Take, for example, V, well, quadratic and quartic part. Now you can just write the equations of motion and solve them. And the solutions to these equations of motion are some elliptic functions. And what you see is that the variable d grows with time, but it grows with time in a benign way. Only the amplitude of the oscillations grows linearly. So there is no collapse. It doesn't hit infinity. So there is some analytic solution, as I said, some elliptic functions. Now, another variable, phi, is just bounded. It doesn't grow. We know now some other benign systems with ghosts, that is benign high derivative systems where the Hamiltonian is not positive definite. But the classical trajectories don't hit singularity, and that means that the quantum mechanics of these theories are also well defined. In this particular case, one can solve quantum problem explicitly, just find Eigen functions. And what one finds? One finds a state in the middle of the spectrum at zero, which is infinitely degenerate, but these states are localized, normalizable. And then there are bands of continuum spectrum on the right and on the left, like that. Now one can consider some modified model. I call it mixed because, you know, if there is no this high derivative term, then it's very well known Witten's quantum mechanics, supersymmetric quantum mechanics. So I add here at the supersymmetric level the term without time derivatives, right? Now, if gamma is there, the second integral of motion is not there, so it's not integral, it's not exactly soluble, but one can solve it, classical system, one can solve it numerically, it's not a big deal, right? And if one solves it, one sees that earlier in the system with gamma equals to 0, the amplitude for the oscillations of D grow linearly. And here it doesn't grow. There are some beats like that. So here gamma is small, so it starts to grow, but then it goes back, starts to grow, then it goes back. So not only phi, but also d, the function d, is bounded. And again, the classical trajectories are benign, there is no collapse, and that means that quantum mechanics is also benign, though in this case it's not possible to write explicitly the Eigen functions of the Hamiltonian, right? Now, there's some mathematical, how to say, harvest from this system. it has some unusual algebraic structure. So that probably I will skip this part because I don't know if you know well the usual supersymmetry algebra. The usual supersymmetry algebra is extended supersymmetry. There are two pairs of supercharges and its Hermitian conjugate, and the anticommutator of each supercharge and its conjugate is Hamiltonian, and Q1 and Q2 can just anti-commute, right? And here it's unusual. First of all, one can write the supercharges, but they are not Hermitially conjugate to each other. That means that the Hamiltonian is also, at least naively, not Hermitian. On the other hand, the energies are real. So this Hamiltonian belongs to the class of these pseudo-Hermitian Hamiltonians, which which are of interest for this community, right? So there are two pairs of supercharges, this pair and the extra pair. And the algebra is complicated. So if gamma is 0, then that's kind of semi-direct product of usual algebra. And some other algebra generated by these two integrals of motion, well, extra integral of motion, and that was the fermionic charge. Anyway, one can write this algebra, and it belongs to, well, there's classification of all super algebra, worked out by Katz, and it belongs to, it has some name. That's OSP 2,2 algebra. Now, this weak supersymmetry I will not touch at all, but what I will tell you now about is what happens for field theory. So if you write just by hand, not without care, some higher derivative field theory, then it's not unitary. The collapse occurs there. But there are some special field theories, and I found this field theory in one time and one special dimension. So that's how it looks at the level of supersymmetric action. That was my starting point, but don't put attention here, just look at the Bosonic Lagrangian, right? So mu is now, takes values 0 and 1. That's the Lagrangian. And if V involves quartic part, it's nonlinear. And the equations of motion, well, I write it like that. So they involve only a second derivatives, but it's a system of two equations of motion for phi and for d, right? The energy is not positive definite. And there are two integrals of motion, the energy and another one, which corresponds to this n, the integral of motion n I talked about before, right? I probably will not go back to show it again, or probably I will. So that was the integral of motion mechanical system. And that's the integral of motion, extra integral of motion in this field theory system. But you have only two integrals of motion, and there is an infinity of variables. And that means that the system is not exactly soluble. And that means that it's stochastic. So one cannot solve it analytically and can try to solve it numerically, which I tried. And what I found is that the trajectories don't exhibit collapse behavior. They stay more or less bounded. So I introduced a finite spatial box to solve it numerically. Try different initial conditions, and that's the typical behavior. So what is plotted? That's the time, and there's the dispersion. So for the variable d, the average value of d as a function of time. So it's positive, it's square root of something, of some square, right? And so it grows. There is some stochastic behavior, but generically it grows, which reminds you the regular behavior in mechanical system, right? This one. Here it just grows and it's regular. And for the field theory, where there is no, well, not enough integrals of motion, it grows, but there is also stochasticity on top of that. I again show this here. So we are close to the end of my talk. And I just reiterate my sweet dream, but now a little bit more specific. So it would be nice if the theory of everything would be a high derivative field theory with benign ghosts. Benign ghosts meaning that there is no collapse. And this theory should be formulated in a high-dimensional space-time, and our universe is free-brain, like a classical solution in this bulk. Of course, I have no idea what is this theory. Well, one tries to write something, always I try, but it's collapsing. So the ghosts are not benign there for the models which I tried. But maybe some clever guy once comes and writes down the benign theory of everything. Okay, that's all. Well, thank you for the attention.
Thank you very much, Andrei. Any questions?
Yes, I have a question, please. This is Joshua.
Yes.
Hi, hello, Andrei. Thank you for your very interesting talk. I have a question and a comment. Maybe first the question about your supersymmetric model, the first one. So there is supersymmetry between bosonic and fermionic states, but for every non-zero, either negative or positive energy state, they are paired. So it seems so that you can define a Witten index as in the usual case.
Well, Witten index, no, I cannot do that because the partition function.
But you can cut off the partition function above and below, and all the positive and non-zero states will cancel. No, only the zero state will contribute.
The zero energy state is infinitely degenerate here. So if you want, if you call zero, what is zero? Zero energy is in the middle of the spectrum, right?
Yes.
You are interested by the states in the middle of the spectrum.
Yeah.
So it's infinitely degenerate. So I haven't studied this question. I think that Witten index doesn't apply here. But I just didn't think in this direction.
So this is a problem of very high degeneracy at zero. It's reminiscent of the Landau levels problem. The lowest Landau level at very high magnetic field is very degenerate. Okay, so so now a comment about the two ways to interpret the Pais-Uhlenbeck oscillator. You mentioned that there is one way a la Carl and Philip, where the second coordinate becomes purely imaginary.
Yes.
Yes, and then there was the other method that you mentioned, where the Hamiltonian is not bounded, but states are.
Joshua, I would say, I would say that these are two different systems.
Yes, of course, two different physical realization or quantizations of the system. I absolutely agree. I just wanted to comment that there is an analog dichotomy also without higher derivative. Just consider, and it's related to the fall to the center problem that you mentioned. So, for example, in the fall to the center problem, you can, even if the system is unstable quantum mechanically, it still admits self-adjoint extension. And the self-adjoint extended system has perfectly well-defined unitary time behavior. Of course, the price is that some parameters lurk in and they parameterize your ignorance of what is really going on at zero. Similarly, just consider the inverted quartic oscillator. The inverted quartic oscillator in one dimension is in one way of interpretation. You can consider it as a special case of the Bender-Bottcher potentials for particular value of the parameters there. And if you impose the boundary conditions that Karl and Bottcher used, of course, you get a well-defined Hamiltonian with a bottom, with a ground state, normalized states, etc., etc. Everybody knows that. But maybe less known is the fact that because the time to go to infinity, now I'm just talking on the real axis, no PT, just inverted oscillator on the real axis, a quartic oscillator, the time to going to infinity is finite, so you have to treat infinity finite boundary. You send it goes whoosh to infinity, it reaches a finite time, and then you have to ask yourself what to do. What's going on with the probability? Again, you can introduce self-adjoint extension, one parameter self-adjoint extension, and get a perfectly well-defined unitary time evolution. And in fact, 25 years ago, I used this trick to deal with the in quantum cosmology with the size of the universe, the scale factor of the universe. So you get a well-defined definition, if you like, of the Wheeler-DeWitt equation, etc., and it works.
Okay, so okay, Joshua, thank you. Probably you cannot comment on your comment.
Okay, thank you.
Okay, may I make a few comments?
Sure,
Okay,
sure.
very quick side remark to Joshua. In an anti-de Sitter space, it also takes a finite time to go out to infinity, just out to space infinity. That's just it's called not globally hyperbolic. So there are such geometries which do what you just described. Now, I wanted to comment to Andrei's talk, of course. I have three comments. First of all, the sweet dream, that's the screen that's in front of us. Do you really mean a higher dimensional flat space-time, or do you mean a higher dimensional empty space-time? The reason I ask that is if there are no fields in the bulk, but there are fields on the brane, the fields on the brane set up a geometry in the bulk. And therefore, you can't maintain a flat bulk if you put fields on the brane. So I think what you might mean is that the higher dimensional space has no fields of its own. Is that possible?
Well, I have in mind indeed like a soap bubble, right? Soap bubble definitely exists. There are some effective fields on the surface, and it exists in flat space.
Well, if the fields on the surface are long range, you need some way to confine the fields so that they're only on the surface.
Just the surface itself is kind of classical solution. So imagine, there are solitons like classical solution, but there are also extended classical solutions, right? And we know, for example, Abrikosov strings. These are lines, also a classical solution. But one can have also some branes, 2 branes and 3 branes. And then they can be curved. Abrikosov string, not necessarily straight. One can curve it. And so without any possibility to write something scientific, I was just thinking about our universe as such classical solution, high-dimensional bulk. And everything which is on the surface is effective. It's not real fundamental fields which we observe.
Okay.
Fundamental fields are somewhere.
Okay, that was only meant to be a technical comment. Now, the second technical comment is, if you look at the Pais-Uhlenbeck oscillator in the realization where the energy is unbounded from below, the wave functions are not normalizable. You had said that they were, but actually, I've calculated them and they're not normalized. Some of them are, by the way. The ones with 0 energy, right where you would want the 0 to be, those turn out to be normalizable. But as you go lower down in the energy spectrum, as you start going towards -infinity.
Philip, you would mean the Pais-Uhlenbeck oscillator with degenerate frequencies?
No, not even non-degenerate.
Then they're just wave functions of oscillators. They are normalizable. I don't understand.
Anyway, I've worked it through, and I'm just making that as a comment. It was also, by the way, it's also in Woodard's paper.
What is in Woodard's paper?
Woodard also noted that the wave functions were not normalizable.
Well, so, I don't understand it. You just write wave functions. Well, you just write wave functions of the oscillator, right?
Yeah. Okay.
You make this canonical transformation. You
Yes.
just write the wave functions of the oscillator, and then you express these functions in terms of original variables. So they are normalizable. I just don't understand you.
Well, I'm telling you what I've calculated. Anyway, that was meant to be a comment. Now, my real concern and the question about the path integral formulation of the Pais-Uhlenbeck oscillator, I have looked at that some time ago. And what happens is, Carl and I had indicated that you had to continue the quantum operators into the complex plane, as you described. But if you want to make the path integral exist, you have to continue the path integral measure also into the complex plane. And so what actually happens is that that without that continuation of the measure, the path integral doesn't exist. And you can see why in Euclidean time, it behaves at large Euclidean time as e to the minus e times tau. But if e is negative, that blows up as tau goes to infinity.
Of course, yes.
So that means the integral doesn't exist.
That's what I also say. There is no contradiction.
But it does exist if you continue the measure into the complex plane. And that's something I have discussed at some point in the past. Okay. That you might find that useful.
Well, that I just don't know. You agree that ordinary, one cannot make the ordinary Euclidean continuation of the path integral. You agree?
Yeah, because the path integral doesn't exist.
Minkowski path integral does exist.
Minkowski you can write it down, but you can't. When you do the integral, you get it's infinite. You need the I epsilon to give you oscillations, to damp the oscillations.
Well,
okay. And you've got to choose the I epsilon very carefully.
Well, okay, that's some fine issue about this I epsilon. There was some paper with numerical calculation of Minkowski path integrals for quantum mechanics, but they did it for ordinary systems, not for high derivative systems. And they did this I epsilon, you're right. And frankly, I just don't know what happens if one tries to do this numerical calculation of path integral for high derivative systems. That's an interesting question.
Okay. Anyway,
but we agree that Euclidean path integrals don't exist. And we don't agree that Minkowski path, you say that it also doesn't exist. And I'm saying that it still has some chances to exist, Minkowski path integral.
Well, if the Minkowski path integral exists and the Euclidean path integral does not,
yes,
the Wick rotation has to fail because of the circle at infinity contribution.
Yes, Wick rotation fails, I agree.
And that, so therefore, if you want, what you will need for a consistent theory is that the Minkowski path integral exists and that the Wick rotation doesn't generate a new infinity through a circle at infinity contribution.
Why do you need Wick rotation?
Because to get to the Euclidean path integral, you can't do it. I mean, that's
yes,
what you...
Yes, but that's what I'm saying, that you cannot go to Euclidean path integral. So there is some very queer, unusual theory where indeed Euclidean path integral is not defined.
Well, I mean, a Wick rotation is you're just rotating the Feynman contour through 90 degrees.
Yes, yes, I don't know how to do
rotation.
And you need the circle at infinity to cancel.
Well, okay, that's Feynman. You want to do Feynman integrals, some perturbation theory and field theory, right?
No. I just want to do Wick rotation. A Wick rotation is a change in the contour.
Yes, but why do you need it? To calculate some diagrams, right?
Yes.
Yes. Now about diagrams that you want to define the perturbation theory, scattering metrics, scattering amplitudes, and field theory. And I don't know how to do that. I just don't know.
Okay.
I told you everything which I know, and maybe this sweet dream was not realized. But well, what I know, I told you, and indeed, in field theory, we always treat the scattering of some excitations over the vacuum, right? And if the vacuum is not there, I just don't know how to do that.
But Andrei, in quantum field theory, the exact Minkowski path integral doesn't exist without any I epsilon description. You always have to make an analytic continuation. That is what Philip says, yeah? Whether you obtain the same result in a Euclidean or Minkowski path integral depends whether you do the Victor rotation over singularities. But I have another question. I think when I met Carl in what was it, Kiev, at those times they told me in gravity you are not even able to write down free theories for spin 2 particles, which are somehow self-consistent. And now you are telling me the people are working on field theories with interactions where they expect that they have some stability or anything. I'm still puzzled how this is possible if you look at quantum field theory where you're not even able to write down Hamiltonians which are bound from below or bound from above. I think this is a great miracle to me. Maybe string theory allows things which I didn't follow up. But what is your dream there?
Well, I cannot say anything about string theory. That's first statement. Second, quantum mechanical system with benign quantum mechanical systems with non-trivial interactions exist. And you can solve Schrödinger equation there. You can study quantum and classical dynamics. I also think, but that's, how to say, subtle, delicate issue, that one can formulate the quantum mechanics in path integral, with path integrals, but never go, never doing this I epsilon. That's indeed a question which I cannot answer. But they exist, this not non-trivial high derivative systems and mechanics exist. Now I shown you that there is also field theory with high derivatives which also exist, at least at the classical level. And then what is it? What is the physics of this 1+1 field theory, high derivative theory, as field theory, I just don't know, because indeed I don't have the tools. We don't have the tools to study it. S matrix is not well defined. I just don't know what is S matrix there. But on the other hand, classical dynamics is benign. What is quantum dynamics? How, what language should one use to describe it? I just don't know.
Yeah, but the problem was always to get rid of the ghosts and all that to get a well-defined theory. And I think we are still not there in gravity, no?
Well,
two comments on these path integrals. I mean, if you take a free particle, a Klein-Gordon particle, and write down a path integral, then you have not a Gaussian integral. You have an oscillatory integral, and you have to analytically continue. And if you have an upside quartic oscillator, if you are exactly with real fields, you are on a zone where the integrals they do not converge. If you go a little bit in the upper complex plane, you get stable solutions, and if you go in the lower complex plane, you get exploding solutions. So it's always you have to live close to the real axis, but not exactly on the real axis.
Well, you repeat this question, and I told you that I cannot give a completely satisfactory answer to this question.
Yeah, if I may just comment, without an I epsilon, a path integral doesn't make sense, because if you look at the integral, the path integral of phi of x1, phi of x2, what's that? What quantum mechanical operator is that equal to? So you might say, well, it's the matrix element of phi of x1, phi of x2. But the path integral phi's are C numbers. And therefore, the path integral phi of x1, phi of x2 is equal to the path integral of phi of x2, phi of x1. And therefore, if you relate the path integral to the two-point function, you have proven that all fields commute, that all quantum fields commute. So the point is, that the integral phi, that the path integral phi of x1, phi of x2 times e to the is is not equal to the two-point function, it's equal to the Feynman propagator. And the Feynman propagator comes with its I epsilon prescription, and that I epsilon is the thing that dampens the oscillations that you would do in the path integral, because you're just doing e to the is, where s is real. And that's an oscillating function. And so from the word go, a path integral is automatically a Feynman propagator and not a two-point function. And that's
well, okay, maybe you are right, Philip. I said everything which I could. I cannot say more.
Anyway, this is fine. But I do think that if you're allowed to dream, you might pursue Carl and I's idea of continuing into the operators into the complex plane, and see if you can't generate that theory as a brane in some higher dimensional bulk. That one, I think.
What theory? I haven't understood. What theory?
That would give you, the one that Carl and I do, where we continue the x2 into the complex plane. That might give you.
But that's another theory, and it's benign, and there is no problem with it.
There's no problem with it, so it might realize your dream.
No, well, it's just another, you see, it's, I think it's just a free system. And if you try to do that for interacting systems, then I don't know how to do that again. For free system, you indeed can go to this imaginary x2, and then you define Hamiltonians, everything is fine. And what? You don't solve the original problem. That's my opinion.
Okay.
More questions?
I have a question. Hello, everybody. Andrei, from the point of view, from the very beginning, you introduced the notion of ghost from your point of view. So you defined it, ghosts appear in the systems for which Hamiltonian does not have ground state. So my very general question is, from your point of view, how to treat Dirac equation?
Well, don't see, well, you mean probably the Dirac equation has also positive and negative energies, right? And they filled up. Yes, but that's a special case because the fermions, Pauli principle, things like that, right?
But if you consider the case of quantum mechanics and the one particle system.
Well, yes, but it's known for Dirac equation. Indeed, you have positive and negative energies, but you have also Pauli principle, and there is interpretation that the negative energies are filled up. I cannot say anything new compared to Dirac. Well, about that.
Okay, and
that's not high derivative system, right? It's not high derivative, but it's first order. It's linear. It's not high derivative, but it's first derivative, not second derivative, but first derivative.
Yeah.
If I may, sorry, can I interrupt you because of this Dirac comment? If I may say correctly, as Andrei said, that the negative energy solutions are interpreted in view of CPT transformations of the Dirac as positive energies propagating backwards in time. Sorry, they're the other way around. Negative energies propagate backwards in time because they are the antiparticles. So, but I don't know what CPT in his formalism means, but Dirac, you could understand the negative energies like this, like all the other negative energies, in fact, Dirac Klein-Gordon. So that's, I don't think that would be the problem, in my opinion.
And I would like to draw also your attention, Andrei, that okay, there is some another example of consistent, at least mechanical system, which is consistent at the classical and quantum level. I mean, the system with high derivatives, but when you consider the system given by the action, which is proportional to the curvature of the world trajectory. So it is possible to see
what?
Of world trajectory. That is, you consider a 3+1 dimensional Minkowski space, flat space, and you consider the particle with the action, which is proportional, some constant multiplied by the integral of the curvature of the world trajectory.
I don't understand what trajectory, Mikhail.
World line. You have
world line.
Yeah, and you write the curvature of this world line. And so, if you consider such an action, so it is possible to see that if you assume that the particle moves with velocity less than velocity of time, so we have problems. The system has no solutions. It is self-contradictory. But if you assume that the speed of the particle is greater than the speed of light, the system is consistent. And it turns out that this is the constraint system. It has five constraints, 5 first-class constraints, and it describes a particle with a fixed massless particle with fixed helicity. Helicity is fixed by the parameter which appears as a multiplier at the action. And at the quantum level, at least in the free case, the system admits consistent quantization. And at the quantum level, this parameter, which appears as a factor in the action, is quantized, and the system describes massless particle with two helicities, which can take integer or half-integer values. That is, the corresponding parameter is quantized, and at least in the free case, the system is consistent both at the classical and quantum levels.
Well, it was difficult. You tried to provide some non-trivial, amount of information. It was, for me personally, it was difficult to analyze it. I don't know. That probably is correct, but I just need more time to understand it.
Okay.
Any more questions?
Andrei, there in particle physics, at least you can obtain nonlinear sigma models out of a linear sigma model, and you have some hope to get a renormalizable theory under certain conditions. I wish you that you can do this by construction. At the moment, you are in hopefully nonlinear models. So maybe you take an approach where you come from a control theory and make it higher derivative by construction, and then you come out with some controllable theory, which might solve all your problems.
Maybe, Frieder, I don't know. Again, I am just exhausted. I told you whatever I knew. And many other things, well, one can study them, but they're difficult to study.
But the nuclear physics make exactly this mistake to sit in a car where they don't know what the machine is. They had from the beginning derivatives in their interactions, and in the end, they figured out that if they start with a linear sigma model, then they can construct systematically models which work. So I think even in gravity, one should do this, work with models which from the beginning are under control, and then step by step make them higher derivative. Then you know what you are doing. But I think you are always sitting in models where you from the beginning have big troubles to understand what's going on. That's my feeling.
Well, anyway, if fundamental theory involves higher derivatives, then you have these problems, right? And I argued that to explain our world in this idea that the fundamental theory is a field theory and higher dimension, it should have higher derivatives, otherwise it's not renormalizable.
Yeah,
So
but before the discovery of intermediate vector bosons, we thought that weak interactions is also such an effective theory with a lot of derivatives, and we were fighting with the normalizability of our theory. Nowadays, with the intermediate vector bosons and Young-Mills theories, we have somehow the theory under control. So getting in from the beginning in higher derivative theories is a really difficult thing. Yeah.
Oh, okay. So you want to write down some fundamental Lagrangian without high derivatives, and then what would you want? Because nonlinear sigma model involves, well, it's not renormalizable, it involves derivative, and Fermi Lagrangian is also not renormalizable, but there is some fundamental theory which is, right? So I just don't know. Well, you want to make a high derivative gravity as an effective theory of something, or what do you want to do?
Yeah, well, the problem is we start with equations which are from the beginning uncontrollable. Yeah, and we had this in the last sessions where we were talking about dissipation and or non-Hermitian Hamiltonians with exploding, exponentially exploding wave functions or decaying wave functions. If you start from the beginning with a Lagrangian which you can control and then continue it to a phase where things get nasty, then you still have control over your system and understand what's going on. And I think this should be the path we should take now in non-Hermitian physics. Not from the beginning sit in a system which is very, very dirty and very difficult to understand mathematically, and then hope that this saves our physics. I think we should start from something which we can control and then get there where you want. Yeah, we in particle physics, for instance, the introduction of scalars or quarks with imaginary masses solved a lot of things which we couldn't handle before we had all these mathematical ideas. Yeah, even the Fadeev-Popov ghost was an idea like this, and I think one should return in gravity to this approach. You start with something you control, a car where you know the machine, and then you go to more and more complicated things. It's my feeling, the strategy to go to gravity and unify it with quantum mechanics. But 15 years ago, when I met Carl in Kiev, the Russian physicists and Ukrainian physicists there said, nobody knows how to write down a field theory for spin 2 particles which interacts and which is somehow under control. And I still didn't find anybody who did this. Yeah, so we need first to write down a field theory which works, and then stretch it to Einstein gravity somehow.
But while it's not done, so one can have different dreams. Look, and one can dream in different direction. One cannot, how to say,
look, I like your dream.
People to dream in different directions. So.
If I may say something, Frida, basically that's what you've just suggested is what I talked about a couple of weeks ago. You just take the Dirac field in an external gravitational field, and then you do the path integral on the fermions, and you generate fourth order gravity. You generate conformal gravity. So in your language, I'm starting out with a theory without direct gravitational interactions. I'm starting out with a second order theory, Dirac fermion, and I generate a fourth order action by doing the path integral on the fermions. Now, that theory was under control. I mean, if you want to say that a Dirac fermion coupled to a gravitational field is not under control, then the whole of modern physics is not under control. I mean, everything. And the answer is, it's under control. You have to do once you've done the first step and you've done the path integral and you've generated the effective action, you've now got to do the integral over the gravitational field.
Right. So you
and
mean
that's where all of these Pace-Uhlenbeck issues come in, and that's why Carl and I invested a lot of time in this theory. It's to make those path integrals exist. And what I mentioned earlier to Andrei, they exist only because you have to continue the measure into the complex plane. Look,
we had the same problem in particle physics with the fermionic determinants in nonlinear sigma models. How do you calculate these quark loops systematically? Yeah? You start from something which you control, and then you end up with a whole bunch of terms when you approach it perturbatively. Yeah?
Mm-hmm.
Anyone else with a question?
No. Anyway, Andrei, thank you for joining.
Okay, thanks for the attention, for very fruitful and interesting discussion.
Yes, and you've given us something to dream about.
I give what?
You've given us something more to dream about.
Ah, okay, yes, exactly.
Thank you very much.
We need in our, how to say, dull life, some dream. Okay, thank you.
Thank you. Thank you.
Thank you, Andrei. Thank you.
Bye.
Bye.
Bye, everybody.
So I switch out, right?